Hello, and welcome to this Cadence webinar. Over the course of the next several minutes, 30 to 40 minutes, we'd like to give you a perspective on how you can address your IC package design scheduling challenges and help to meet those challenges using an advanced analysis approach that features InDesign analysis. So myself, Brad Griffin, who am a Sigrity product manager, and my colleague Andy Hawes, who is a Sigrity product engineer, will give you the guidance on these techniques. We start the presentation off stating maybe the obvious, that the IC packaging world has changed quite a bit over the past several years. We've gone from a world where certainly just delivering a signal from a chip to a printed circuit board through some kind of potentially ceramic carrier, maybe using a lead frame type package, was really just a necessary evil. And the only objective was to avoid negative impact on the chip. Didn't know electrical and thermal problems. But today, the package itself is actually differentiating technology. I've spoken to many customers who say they really look at the way they design their package as important as it is the way they design the actual semiconductor itself. And that has to do with the fact that we've gone to a more advanced packaging substrate that may include using a silicon interposer, stacking die, having multiple die within the package. It really creates a phenomena in itself in how to make all the signaling and packaging power delivery work within the package. But then, of course, it needs to work within the entire system. So this is what's contributing to this world of more than more. And we like to discuss how you can make that whole process, that whole design process, more efficient. And the way that we expect that you can do that at Cadence is by being part of a complete multi-physics analysis of electronic systems flow. And while we'll be talking quite a bit today in this area here of IC packaging, certainly want to make sure that you understand that we extend over in the chip, in the printed circuit board, and provide a full level of solution from power, thermal, EM, CFD, signal integrity, and we have our Optimality Intelligent System Explorer, which actually allows you to use AI technology, AI/ML technology, to truly optimize the design early on in the design process. But today we're going to focus on the SI, the signal integrity and the power integrity approaches, and how to use that in the InDesign world. So from an InDesign analysis perspective, this is where most of the webinar will talk today, but just want to keep your mind thinking that what do you do after InDesign analysis? Certainly for IDA, InDesign analysis, impedance and coupling, the most basic technology lets you look very early to see if you've created some situations where you've got signals that are routed too close together, or you've maybe routed over some gaps in power planes. You've created impedance discontinuities. There's no models required to be able to detect those kinds of problems. If you want to go a little bit further and see what the signals might look like, if you could actually probe it in the lab with an oscilloscope, the reflection and crosstalk technology that we have, that's going to ask you to require some IBIS models. Of course, we'll provide default models in case you don't have IBIS models. This analysis is done with the most basic interconnect modeling. You can actually get more sophisticated if you want, but because we put our focus on getting you quick results that you can respond to and make changes and actionable analysis while you're designing, we use the most basic interconnect modeling. We do like to encourage our customers to have both the designer and the analysis expert concurrently connected to the same design. And that way the analysis person can be performing analysis while the designer is actually designing the board. As the design becomes a little bit more mature, reaches closer to the sign-off stage, we'll certainly go beyond that basic interconnect modeling using our hybrid solver or our full wave 3D field solver Power SI, Extract IM for the hybrid solver, or Clarity for the 3D field solver. The IBIS models become more sophisticated. Make sure we're using power aware IBIS models so we can look at simultaneous switching noise when it comes to memory interfaces or any bus signaling, and or typically for serial links, but as well as for DDR signals. We need to provide some kind of equalization. That's done in the manner of IBIS AMI models. Helps us look at both DDR and signals like PCI Express. And ultimately, we put together the full source driver to the full receiver sync, all the various pieces of interconnect along that path. Could be the interposer, a package, a board, could even be a mechanical connector, another board, another package. All this needs to put together to provide a complete signal integrity sign-off flow. For power integrity, it's not that different. It's just we're doing, the focus is on looking at the metal power planes instead of the individual routed traces. For InDesign analysis, we provide a power tree technology, which lets you very quickly look at how the power delivery network is connected. You may have hundreds of pages of schematic. The power tree lets you very quickly see that you've got the source connected as components and what the any need to be able to change voltages. You can see how that happens. Ultimately, we want to help you run IR drop analysis as you're actually creating the actual package, and help you make decisions on decoupling capacitor placement. Make sure you're placing those capacitors close enough so that they're useful. And again, we encourage the multi-user environment, both designer and analysis expert, being able to look at the same design concurrently and be able to make those changes. All of this helps to reduce the ultimately helps to reduce the design cycle. As far as the package becomes more mature and is getting closer to the final sign-off, analysis evolves beyond just pure IR drop to electrothermal co-design or co-simulation, and looking at the decoupling capacitor optimization. Do we chosen the right values for the decoupling capacitors? And we can actually extract the power delivery network out using hybrid solver or 3D full wave solver technology. With those extracted models, we can put it into a flow where we look at the power delivery networks of boards and packages and interposers and all those various different pieces together and see how it goes from the actual source to the actual sink. We can look at both the IR drop, the AC analysis, making sure that we're meeting our target impedances, and we can look at voltage ripple as well. And ultimately, we like to encourage our customers to put this into a full 3D environment where you see the board, the packages, any fans can be considered as well. We're looking at the electronics cooling and make sure that the system is going to work from a thermal perspective. So with that, I'd like to hand it over to my colleague, Andy Hawes, to talk about specifically how we do the InDesign analysis of an IC package using our latest InDesign analysis technology. Take it away, Andy.
Hello, everyone. And again, thank you for taking the time to join us today. As Brad promised, I'll be providing a demonstration of Aurora for Allegro X Advanced Package Designer. But first, I'd like to provide some additional detail on the overall product as well as individual workflows. Aurora for APD is a recently introduced product from Cadence that provides a broad set of simulation capabilities to package designers. We call this capability InDesign Analysis, or IDA. IDA is a guided process of design setup, simulation, and results analysis that is provided in the form of a sequence of key steps without forcing a rigid sequence upon the designer. In addition to easy-to-interpret tabular analysis results, Aurora's Visions overlays provide an immediate and intuitive visual rendering of those results directly onto the package layout. And because some simulation tasks can be rather compute-intensive, Aurora for APD supports multi-core and distributed processing, so designers have the bandwidth to analyze as part of their design process. Finally, while some may not be familiar with S parameters and such, Aurora allows the user to complete complex tasks by providing sensible default settings and models and by taking care of advanced steps such as 3D solver port creation and post-analysis port de-embedding. Within the APD canvas, Aurora provides easy-to-use access to a wide range of simulation and analysis capabilities, all powered by Sigrity technology. Users can screen package designs in novel ways to accelerate the design process by catching issues earlier and natively editing the designs without switching tools. Users can screen package designs in novel ways to accelerate the design process by catching issues earlier and natively editing the design without switching tools. Sigrity Aurora quickly and clearly provides design engineers with actionable feedback against their design iterations. The supplied workflows guide users with step-by-step setup and execution. By following the workflows, infrequent users don't need to learn or relearn a new GUI or use model. Sigrity Aurora for APD is designed to enable rapid turnaround, catching potential problems and bringing to light otherwise overlooked situations. Indesign analysis enables the package designer as well as the signal integrity specialist to find problems earlier in the process and shorten the design cycle. Let me quickly introduce you to the available workflows. The purpose of the design setup workflow is to walk the package designer through the necessary steps to ensure accurate results from the Sigrity simulations that enable Aurora's workflows. The workflow guides the user through critical setup categories such as stack-up definition, component classification, signal and power net configuration, ball and bump definitions, and default and vendor I/O simulation models. The impedance workflow allows you to quickly identify single-ended or differential nets that are out of spec or out of the norm for the nets being analyzed. Within the simulation results table, the user can identify nets that have the lowest or highest min, max, or typical impedance, which can expose design problems from plane voids to stack-up issues. Impedance visions can be enabled to transfer the table's color coding directly to the interconnect, while selecting an element in the table will bring it into view on the canvas. The user can adjust the color scale to further highlight the problem areas. Coupling analysis locates the nets and portions of nets which have the greatest coupling with neighboring interconnect. Because coupling analysis doesn't use time domain simulation, it doesn't need I/O models and can identify potential crosstalk issues very quickly. Taking coupling a step further, the crosstalk workflow produces true crosstalk values in all neighbor mode for worst case or each neighbor mode to locate specific crosstalk events. Settings such as minimum coupling coefficient and geometry window enable the user to minimize simulation time and maximize the efficacy of the analysis results against the design at hand. With reflection analysis, a time domain simulation is used to produce automated performance metrics as a function of the rising and falling edges that each net experiences. Measurements include ringback margin, overshoot, switch and settle, and propagation delay. With the IR drop workflow, you can catch voltage drop and current density problems before the physical design is complete. Using configurable IPC or manual thresholds, current density issues in vias, traces, and planes are captured in both table and visual forms. Users can import constraints, models, and setup details from Sigrity PowerDC and PowerTree. For larger designs, distributed computing is supported. Return path analysis produces a sortable tabular report of the return path quality for all signals that the user chooses. Once the worst case nets are identified, the user can then generate net-specific visions to highlight the weaknesses in these return paths to quickly understand and take corrective action. Because the results of each net are normalized to their ideal return scenario, batch analysis of widely ranging net groups is possible. No simulation models are required for this workflow, so setup is a breeze. Finding and solving power delivery weaknesses in your package designs is the purpose of the power inductance workflow. Capacitor to IC view mode produces a decap loop inductance table that highlights weaknesses in power pin decoupling, while IC power pin mode characterizes the self and total inductance as seen by each IC power pin. The results are captured in tabular and graphical form and can also be saved to an HTML report. The Extract IM workflow brings Sigrity Extract IM Electrical Performance Assessment to the package designer's workspace. Both power and signal net parasitics are reported, providing valuable insight to the designer while also visually highlighting potential design problems that may warrant closer inspection. Lists of nets can be saved for reuse and shared with other workflows, which makes for an efficient closed-loop design implementation process. The topology extraction workflow translates the interconnect and stack-up information for a user-selected net or diff pair into a topological view in Topology Workbench. Here, users can perform simple time domain simulations, parametric sweeps, and can also develop constraints that can be used to drive and verify implementation. Additionally, the View 3D Geometry feature allows the user to quickly preview the selected interconnect before it is extracted. Prior to the Aurora workflows, full-wave 3D interconnect model extraction was a disconnected and confusing process. The interconnect model extraction workflow allows any APD user to perform this task. With IME and supporting PowerSI or Clarity licensing, you can choose to extract a single net, drag select multiple nets, or share a list of nets with other workflows. Simply choose the solution frequency limits, reference net, and set up distributed compute options for larger jobs, and start the extraction. The resulting S parameters can be viewed in return, insertion, and crosstalk modes, and can be shared with your signal integrity specialist or sent directly to Topology Workbench, where it can be used in limitless simulation scenarios. And finally, I'd like to highlight a few of Aurora's performance enhancers that really pay off in larger designs. Aurora's high-performance computing support allows the user to target most workflows to the desired level of CPU resources, more cores for faster results. With supporting licensing, there is no CPU limit, and more complex simulations can be distributed to multiple hosts. Automatic design cropping trims the database of unnecessary nets and design areas to speed each simulation type while also reducing memory requirements. And for cases such as the IME workflow in the previous slide, fully automatic port creation and de-embedding are big time savers, and this savings multiplies as the complexity and size of your designs continues to advance. Okay, that completes my introduction of Aurora for IC packaging. And now for a brief demonstration. Okay, let me start by launching APD. We'll use the SIP layout bundle that'll allow us to run the Aurora workflows within APD. And we'll start with a package design that has two flip chips. You can see it here, and 6 conductor layers. And let's take a look at this in 3D. And you can see chip 1 and chip 2, as well as the solder balls. There's signals between chip 1 and chip 2, as well as each chip and the solder balls will be analyzing various parts during this demonstration. So let's go ahead and launch the Workflow Manager. And the Workflow Manager provides a series of flows that guide you through the key steps of any analysis task. From top to bottom, generally speaking, and you can choose from any of the number of workflows that are included with Aurora, 11 here. And let me start by setting the key DC voltages for the various power nets in this design. We just simply multi-select and assign a voltage and select the next. And when we're finished with the last one, we click OK to commit, and we're done. Let's go ahead and refresh the design data. And there's one example, but the workflow includes everything from stack up data to signal integrity models to solder bumps and ball dimensions. All right, so let's go on to some analysis. I choose the impedance workflow. And the impedance workflow allows us to screen the signaling nets in the design for impedances that might be out of our range of expectation. So we begin the analysis process by choosing the nets that we want to analyze. We can do that by area select. We can click on a single net or shift select and move a group of nets, double clicking on a single net, etc. We can easily move those back and forth. or we can choose a list of nets. And that's what I'm doing here. And in the simulation options, I'm going to enable coplanar mode for the signaling traces. And that'll include neighboring plane shapes when it comes to impedance calculations. And I'm going to disable the design cropping option here since this is a very small design. And we can go ahead and start the analysis. This shouldn't take long. And the simulation is done, and you can see here we have the ability to save the simulation results and reload them later to save us on simulation time. I used a net-based analysis mode here, and I could have chosen directed groups, and we'll come back to that at a later time. Let's go ahead and view the impedance tables. And right away, I see something that concerns me. It looks like every other net has a different impedance alternating here. I sort by my typical column. I can see two different impedances, 61 ohms and 78 ohms. And as I scan through these, I can see here that my blue or my 61 or 62 ohm are on layer 3, while all of the reds are on layer 2. And so let's take a look at that in the design here. Let me rearrange stuff a bit and turn our visions on. And as I double click on one of these items, it's going to bring that item into view. And here you can see the blue and red that I was talking about. And again, the blue nets are of the lower impedance, while the red nets are on the higher impedance, as you can see on the scale to the right. But let me give you a little bit of a explanation as to what's going on here in the stack up. You can see layer 2 and layer 3 are adjacent to the top layer. Let me turn the visions off. But the top has no copper in the area of these nets. Layer 4 is a ground plane or a reference layer, but layer 1 or the top layer is open in that area, and this is the reason that the layer 2 routes are of higher impedance. And if we want to avoid performance issues, we're going to need to take care of that. And I think probably the best thing to do here, and we can either make the top layer a shield layer, or we are going to need to shift our signaling layers down. And in this case, I'm going to open a design where we've done the latter. The updated version of this design has the signal layers shifted down by 1. And I'm just going to load previously saved settings rather than manually configure the workflow this time. And we can go ahead and start the analysis. And under this case, and when the simulation completes, we should see indeed, based on the better referencing, let's go ahead and pull this up a little bit. We can see that our typical impedance is consistently the 70 or the 61.9 ohm value. And there are some excursions outside of the 61.9, and those events are the result of fillets and lead-ins to vias. And that's the purpose of the typical column, is that it ignores those brief excursions. Okay, so we solved our impedance issue. And normally at this point, I'd be talking about coupling and crosstalk workflows. But to keep things moving along, I'm just going to recap in slide form. Coupling, just like the impedance analysis we ran, does not require signal integrity models. It uses field solve techniques to give the results. While crosstalk uses IBIS type models, just like the reflection flow that we're going to move into right now. So let me change to the reflection workflow, and we'll load the settings quickly and run a simulation. And since I didn't specify IBIS models for this simulation, the built-in defaults will be used. which helps us stay productive with minimum setup time. Also, I can choose here the interconnect model for routed or for unrouted nets and specify the stimulus for the simulation that takes place. So if you're familiar with IBIS type simulation, this is exactly what happens here. Okay, so I have results to look at, and we can see that things are actually quite uniform from settle times, switch times, the overshoots, ringing. They are all very similar, and that's pretty obvious here. And it's because it's because all the nets are almost identical in routing. So let me quickly show you the waveform viewing capabilities. As you can see here, very easy to view the simulation results of each of the nets that were chosen. So that takes care of reflection analysis. So let's move on to IR drop workflow. And since we're working with the same design, we just switch to the new workflow and continue our work. And after I load some basic settings, we're ready to set up our IR drop analysis. And for an ad hoc scenario, all we need to do is set up our VRMs and our sinks, which would be the loads in the design. Here I'm setting the BGA pins as the source or the VRMs, and chip 1 and chip 2 as the loads or sinks. And we'll go ahead and set the drain current or the sink current at 0.9 of an amp each. The tool automatically uses the DC net voltage as the operating voltage for this IR drop analysis. Kick off a simulation, and we should have results very quickly. Note that I've disabled the ideal ground mode, so we are simulating the ground as well. And here you can see the results, and you can see if I sort here by IR drop, we'll see that I have a fail condition. Selecting that expands further into the net that is failing. Expanding further, I can see that my problem is with chip 1 pin 209, which has an excessive IR drop value based on defaults. And selecting on the worst violation, chip 1 pin 209, takes us right to that location. If I enable visions, I can see that IR result data superimposed graphically directly onto the artwork on a layer by layer basis, red being the peak IR drop value within the current view. And let's take a look at current density. And we also have a violation here with a couple of vias. And we are exceeding the threshold defined in the settings. And this is the same area that we were looking at for IR drop. In this case, it appears that we have a single via feeding that circuit, and that is exceeding the via's current density limit that is part of the user settings. And to look a little bit closer here, we can see the current direction arrows are confirming that indeed that is the one path feeding that device pin. So we found two different problems, which will likely take two different solutions. So let's first solve the IR drop issue by widening the routes, the connect lines that are in view currently. Change the visibility settings to make this easier to access. And then we'll just do an area select to change the widths. Oops, I selected a little bit much here. Let me undo that. Need to change our selection here. Deselect. And we'll go ahead and right click and change the width of these from 13 to, let's bump them up to 30 mils in width. And we should be okay. I don't think we're going to have a problem here. And we can go ahead and start the analysis again. And And hopefully that helps us out on the IR drop front. But it will not do anything about the current density issue. So let's take a look at the IR drop. And you can see here that the voltage drop issue is solved, but that did not take care of the current density issue at the vias. So let's go ahead and load an updated design that has some extra route and an extra via in hopes that we can divide that current from the initial one via into two separate paths. And let's bring up our results and see how our corrective action fares. And so the via again is right there. And let's reset our visibility. I could have saved that off and loaded it. Would have saved me a little bit of time. And the first thing we see here is that the IR drop is no worse off. We haven't heard anything there. And let's switch to current density and see the impact. It looks like we've got things taken care of. Our failure on those two vias is solved via current sharing, no pun intended. And now we can see two paths that are showing the current. Let's turn on the vectors, and we can now see two distinct paths supplying power to that particular load. So in summary, for IR drop, we identified two different problems. One was a voltage drop issue and the other a current density issue on a via, and we solved both of those problems in pretty short order. And this was all performed within APD. All right, next up is return path workflow. And I've opened a new design. Let me quickly show you this design in 3D. This is a flip chip, actually a stacked die. We've got wire bind on top and flip chip underneath, as well as 4 decoupling capacitors on the top, as you can see in the blue. And we're going to take several analysis steps on this design in the next few workflows. And the return path workflow uses directed groups for selection of similar nets. And directed groups allows for easier and more powerful selection and analysis of similar nets, like the bits of a data bus or address bus or things of that nature. But I've already filtered the net list down, so I'm going to quickly load those. And again, for a larger design, we'd want to enable distributed computing and also enable the crop area by selected nets, which would save significant simulation time. But to move things along, I'm going to load the results. And they're pretty straightforward. I've got 4 nets identified in the directed group, and as you can see them right here. They're all similarly routed, similar length, but the first 2 listed here, scan in 1 and 2, have a higher value for the quality factor. We're really aiming for a value of 1 here, which would be the case where the loop inductance of this net is equal to the loop inductance under an ideal return path scenario. And let me highlight these nets so you can see them real quick, one at a time. They're all generally equal in length and similar in routing, but they radiate off in different directions from the die. And so they should have similar results, but let's do a simulation of this return path and view those in a Visions format directly onto the layout. So as we cycle through the layers, we run across the ground plane that is the reference for our selected net. And so we can see a graphical representation of the return path, but something sticks out as we zoom out a bit, and that is part of the return path. And we also see a bottlenecking because of this moded off area. And that is the cause of our quality factor issue. The closest ground pin for that signal net is behind the mode. So let's load a corrected design where we, in this case, will remove them out. But another solution obviously would be to add a ground pin if it's not too late to do that. Um, and we've loaded the results, and you can see right here that the scan in one signal, which was the worst, is now one of the better uh, signals as far as return path. And we can see that result. And of course, the bottlenecking is gone because that mode has been removed. This problem would not have been found by an impedance check or even time domain simulation. So let's go into power inductance, which is another easy workflow to set up and run. Basically, choose your power and ground nets, and then identify the IC and decoupling capacitors associated with that IC that you'd like to analyze. I'm going to load the results to make things quicker here. And because this is a very simple design, we have only 4 capacitors to analyze and view here. And we get results in loop inductance. We have 2 different view modes, capacitor to IC and IC power pin. And here we're viewing the capacitor to IC results. And we can see that we have color coding based on the loop inductance from the capacitor point of view, and that includes the path to the IC. And so we have routing here as well as the distance from the IC having an impact on this result. So let me load an updated version of the design, which has relocated that capacitor more closely to the IC, and also has an improved routing of that capacitor to the planes. Load the settings as well as the results, and view the results table. And we can see that C1, which was, again, the worst by far in performance, is now one of the best with the lowest with one of the lowest loop inductance values. And similarly, IC power pin mode views the inductance from the IC's point of view. Lower inductance is better. In this case, we have self-inductance and total pin inductance, where an injected current is shared into multiple pins versus a single pin. And finally, let's create a HTML report, which backs up all of our simulation results in both modes, as well as the graphical results. Spread this out a bit. Looks like we're missing a little bit. There we go. And of course, we save that off for future reference. Okay, and on to the extract IM workflow. This workflow uses the Sigrity extract IM engine to provide a quick parasitics report for the signals and power pins in the design. Okay, starting out in per net mode, I'm going to just select the top row of wire bonds, which includes a power and ground net, to be analyzed. I'll load the analysis results to make things quicker. And here in the table, you can see we've got very easy to read report for resistance, inductance, capacitance, delay of each of the nets with respect to ground, including the power net. And switching over to per pin mode, we get the same type of results, but this time against the power and ground nets. So here we're limited to resistance, self-inductance, and total inductance for power or ground. And double clicking on any of these rows will immediately cross probe to that location, to that exact pin where the item is color coded according to the vision type that you choose, in this case, resistance. And that sums up the extract IM electrical performance assessment workflow. Let's move on to topology extraction. And let me show you the system configuration editor first. This allows you to logically link multiple designs for extracting combined topologies into the Topology Explorer environment. It's very simple. In this case, I'm combining 2 identical package designs, or nearly identical package designs, by the I/O component, which is the ball grid array itself. Simply identify each design, the component by which they're connected, and make the assignment. And it's that simple. I'm going to go ahead and cancel out of this form, as we're just going to deal with a single design and extract a single net for expedience. Select the net and OK the form. And we have the opportunity to preview in 3D to make sure we have the correct net before we run the extraction process. Close that. And we also have a couple options on what to do for unrouted interconnect. So let's go ahead and start the extraction and take a look. And you can see we've got pretty straightforward topology. Let's zoom in a little bit. You can see the driver, or one end of the net, and we also have the wire bond model. And every segment of the interconnect, including each via or micro via as we go from one I/O to the other. So we can do several things with this topology once we've extracted here. Assign a transmitter model or driver model to one of the devices and set up our analysis options. Let's change the bit rate to 100 megabits per second and kick off a simulation. And in no time, we have some waveforms. Of course, we can manipulate the graphics any way you like. Save the waveform off. But we can also go in a different direction with this process. Export a constraint topology, and we can then assign constraints to this interconnect. And I'll create a relative propagation delay constraint, set it to 2 nanoseconds plus or minus 5%. And here we have the opportunity to save this or this topology, or export or feedback the constraint to a constraint manager, or save it as an EC set file. Okay, last but not least, the interconnect model extraction workflow. The IME workflow really brings a lot of advanced solving power directly to the package designer. With appropriate licensing, you have access to PowerSI's hybrid solve capabilities, or Clarity 3D FEM's full wave solver for unmatched accuracy. For the webinar, I'll choose PowerSI, and we'll select a group of nets using the import list capability. Looks right. Just to be sure, we can use the 3D view. And we're going to capture the bond wires and solder balls as shown. And we'll adjust the maximum solve frequency as appropriate for this particular design. Make sure the design cropping is enabled and start the simulation. And when the simulation completes, regardless of the engine that we chose, we'll end up with an S parameter that represents the full coupling and modeling of the group of nets that we had selected. And here we're viewing insertion loss. But let's go ahead and take a look at crosstalk. Let's see what we see. Okay, we have some peaks at various frequencies, but we have a really high crosstalk in this area. Let's take a look. Okay, well, these are two legs of a diff pair. That would make sense. Okay, well, we've created our S parameter that is in the form that is consumable by Topology Explorer. And so we can make use of it there as you would with any other element in that environment. Okay, well, that ends today's demonstration. In summary, Aurora for Allegro X APD enables package designers and signal integrity engineers to quickly analyze their designs through a guided process and produce actionable results to yield a better quality product in a significantly shortened design cycle.
Thank you, Andy. Great demonstration. Before we open it up for Q&A, just want to take a few minutes to talk a little bit about what happens after the InDesign analysis, our complete sign-off solution for multi-fabric, signal integrity, and power integrity. Certainly, Cadence has the design tools for package and PCB, interposer design. Just want to show a couple of examples here of where we put a package and a PCB together. This is actually a design that's done by our Cadence IP team, where we have a PCI Express interface being connected in the package to the board. We're able to do that simulation of the entire package and PCB structure. Similarly, over here on the right, we have an example of our GDDR6 package and a GDDR6 PCB, and being able to combine those together and perform extraction of the two combined fabrics together. Showing these as an example, in reference to today's today's webinar, you might consider the idea of an interposer and a package being extracted together as a single unit to be able to provide a complete reference model for that, what happens inside the package. Some other ways that you can utilize our technology for power integrity. Again, we have the ability to place together all the different models for a power delivery network, whether it be for the voltage regulator module connecting up to the board, going to the package, into the interposer, and we can even extract the chip model using the Voltus chip extraction capability and putting together the full power delivery network, allowing us to be able to look at any voltage ripple associated with the power delivery network. And from a signal integrity perspective, very similarly, using the Sigrity System SI technology, we can put together a complete model for all the interconnect from the board and the package, and then connect IBIS models. In this case, we're using memory IBIS models to connect to that interconnect model, and then look at the receiver, the destination, the voltage, the memory controller, to be able to read and write and look at the data flow in both directions, read and write for a multi-fabric board package. This is showing the idea here of being a stacked memory going through to silicon interposer to the memory controller. So with this, we'll wrap up our webinar. Just as a final messaging, today's discussion has helped you seen how we can shorten design cycles in InDesign analysis from the IC packaging perspective. And certainly when it comes to final sign-off, we believe that using the Cadence technology, you can reduce the iterations and design with high confidence. Your signal quality requirements can be met accurately and efficiently, being able to model the interconnect across multiple fabrics. And by introducing our thermal aware power integrity analysis technology, you'll be able to produce quality products and reduce field failures. I believe this should be interesting to all of you that are attending today, and I encourage you to contact either Cadence or your Cadence channel partner field representative to get more information on how you can be utilizing this technology in 2024. Thank you very much for your time, and we'll open it up for questions now. Thank you.
So with me is Andy. Just want to check in. Andy, you there?
Yes, I am.
Okay, great. So we do have a few questions, and we have about maybe 7 to 8 minutes of time. So I want to continue to ask people to continue to type in questions as they think of them. The first one I have, Andy, this is pretty straightforward. I think one of our viewers says, this looks great for IC package design. Does this work for PCBs also?
Yes, absolutely. Yeah. In fact, the solution came out on the PCB side first, and we've more recently moved it to the APD side. So the majority of these workflows are available on PCB as well, and there might be one or two that are on the PCB and not on the packaging side yet.
Yes, and of course, there's a few on the packaging side that are package specific as well.
Exactly.
Right. So we do have two different products, one that's specific for PCB and one that's specific for IC package, but in general, they are the same functionality. Just we wanted to make sure that as a package designer, you were getting package specific information and options, and the same thing for PCB. Andy, apparently we have some people that are familiar with a number of different Sigrity tools, Sigrity engines, and they mentioned, or they say that you mentioned Power SI and Clarity in, I think you're probably talking about the interconnect model extraction workflow at that time. They're asking, are there any other Sigrity engines being used in these workflows?
Yes, actually, clearly the extract IM workflow is based on the extract IM engine's electrical performance assessment flow. There's optimized PI and power DC are used under these workflows. Of course, the speed gen and speed sim simulator is the simulation under the IBIS type simulations. So there's quite a, and then of course, well, we've got some other flows coming that'll go broader than that as well.
Yeah, I think that's the key here, is that while maybe we didn't say it over and over again, these are Sigrity engines underneath the Allegro, either IC package or PCB design canvas. So you're getting the true benefit of the Sigrity analysis technology being available directly from the design canvas for Allegro PCB or Allegro's package designer. We have one more here that I want to ask. It's not particularly clear to me. Maybe the two of us together can kind of brainstorm on this one, and if we're not getting it, then we can respond to the person asking the question directly. They ask, will there be any discussion on the build/development of the component/element models that are then integrated into the system modeling analysis demonstrated through this webinar?
I was thinking that was leading to the solvers question, basically the same thing. What technology is used under there, which I kind of we just answered, but I don't know
Yeah.
if you've got any other ideas.
The only, I mean, they mentioned component/element models. I think maybe there's a chance, because a lot of times when we get into the 3D extraction world, people are wondering about detailed models for 3D components. Could be, inductors, capacitors, maybe even talking about a mechanical connector that would be connected to a PCB, or put to a package, potentially even a socket that you would want to model. So that's a little bit outside the scope of this InDesign analysis, but certainly as you get into the more advanced sign-off technology that we talked about at the end of the webinar, we have the ability to model all those. So we didn't quite get that right. Hopefully we can, we'll check in directly with the person who asked the question to see if they need any more detail on that. Another one I have here, Andy, so about a few more minutes left, is
That's the same questioner. I'm sorry, the questioner tagged on additionally to that original question. So he's asking about vias, wire bonds, and trace parameters.
Oh, okay, very good.
Yeah, and so all of those, extract IM is specially designed to include wire bond modeling. So is Power SI. And of course, 3D FEM, all these things are, depending on the workflow that is chosen, you have a speed versus performance trade-off, or I'm sorry, speed versus accuracy trade-off, usually. And but we have the options to get as accurate as you need to in any of these.
Yeah, that's exactly right. So I think for the questioner, we do make maybe a few assumptions in the InDesign analysis for the purpose of being able to get actionable results back quickly to the designer. But as you get into the sign off, then we can, depending on whether you're using the hybrid solver or the full wave solver, we can get you very accurate, detailed models for vias, wire bonds, trace parameters, and so on. This is kind of an interesting and maybe even a little bit awkward question, Andy. Somebody's asking if they can run this tool or run this, the technology that you were demonstrating, if their design is from a, I'll just put it this way, from a competitor's layout tool rather than a Cadence layout tool.
No.
Yeah.
No, I believe, and somebody else asked if there's any, if the designs are available, if there's a rack. The two designs I have were made internally, and one of them may already be in a rack. We need to look into that. I need to look into that and see if we can make these available if they aren't already.
Right. Yeah. So I think, the only thing I can say about the, um, if you design in something other than Cadence, is there are some other tools that provide, I would say, the similar level of analysis, but it's not directly on your layout canvas. It's going to be in the Sigrity analysis canvas. And so if you're really interested in learning more about kind of the quick results, sort of a screening type tool that can be used. We can translate designs into that environment from IPC 2581, from ODB++, number of different formats. But there's no way to do the actual InDesign analysis unless your design is actually designed in a Cadence layout tool.